That's what it works basically.
This is pod 2. That's Geeth, by the way.
Hello.
AJ.
Yeah. So Geet is going to be the victim of learning maths today.
I know. What a tragedy.
What a
Yes,
tragedy.
it is
What's
a
the time
tragedy.
right now?
Who even knows?
12:15.
Pretty normal time to be in the library.
Yes.
Very true.
So, Geet, what do you know about spherical coordinates?
Well, I mean,
You
they
know
just
nothing.
work. Yeah, exactly. I know.
Basically,
nothing.
you know nothing.
I know nothing. Yeah.
So, what is our issue? We want you to be able to see only a few pictures at a time. Like
Right.
if you have 2,000 pictures on the screen, do you want to see 2,000 of them all at the same time?
No.
If you have 2,000 images on the screen, especially on the map view, it's just going to be a pain for anybody to go through.
Yeah.
Yes.
This is be very
And-
bloated.
Yes.
Do you want the merging to be like all the images are cluttered in one place and the rest is empty?
No. It needs to be a good distribution of what it actually is.
So Geet is pretty smart. He knows the constraints that we have.
That's a great assumption, by the way. Geeth, are you pretty smart?
Well.
Let's see. Okay.
Just remember, we're the one interviewing you.
Right.
Oh shit. Oh shit.
Yes.
Yeah.
Pressure's on, man's on the hot
Pressure's
seat.
on.
True.
Okay.
So, what we've had to do,
What are we doing, by the way? So, what are we explaining him? What's the main bit of the system that we're trying to get
Well,
Geeth
he
on?
just said the problem.
so we want to
statement, right?
create a way for us to merge the exact correct set of images such that no matter what the user does, it feels like the images are all over the screen. They shouldn't be in one place and they shouldn't be sparse, they shouldn't be too dense. They should be dense in a way that the user just sees all the things that they've done in their life.
Let's put some visuals to this. Can we have this on the phone?
Yeah.
So basically what I'm hearing is we have to have a very interesting way to cluster the annotations on the map and have it be passed out in a way that does not have bloat, where it's not too cluttered, but well distributed enough.
Simultaneously, yes.
But well distributed enough for it to be a good viewing experience.
And so here is our clustering algorithm. You can see how images are created on the spot, and how they're well distributed around the screen.
How many images are these? Can we zoom out?
These are almost like 4,000 images.
Let me see the stack ones. Oh, that's about 4,000 images. And go back in. And there's zero lag, by the way.
All of this has to happen instantly. The user shouldn't even notice that there are 4,000 images.
So I just had a question. How is it possible that you know? Because when I'm looking at this image in the center, right?
Yes.
If I move out, let's say I move it to this point, and I zoom in at this area, this image is consistent everywhere. How are you having that? How do you know that this is the image to be at the top of the zoom out level?
So, we just make sure that the most recent image is always displayed on the top, because we felt that people want to see the most recent images more than they want to see their older images. But of course, when you want to see your older images, you can super scroll back through time, and you can see the most recent images going away and the older images coming up, and you can.
Let's show
see-
them super scroll.
So,
Let's put a smaller date range maybe.
oh yeah, this is almost a full year date range.
Yeah.
Super scroll works best for a week date range, though it can be made to work for any date range. So let's do February 3rd to March 3rd.
I wasn't in Seattle. Just super scroll forward in time. So he's just long holding on the screen and he's just
I
dragging
think we
it
are ahead of real time. Like
Oh yeah, okay, when 2025.
April 2025 hasn't happened yet, maybe.
Yeah.
Kind of sus. So let's just watch the animations. The images are just moving freely. You can see all the things that you've done over this time. And we can try a smaller date range. Let's try almost a week date range this time. Now in a week date range you see much fewer images. That's good because you see it changing even faster.
There's a lot of action happening over there. So how are we
Shivan's
able to do
been doing
this?
a lot of things.
So how are we able to do this? How do you have time effectively as a third dimension? How do you make sure that clustering works? How is this so seamless? How is there no lag on the entire system? What are you doing to get this done?
So we have created a system where the images are clustered in such a way that even when after you apply a filter to the clusters, the images still seem very spread out. That was our main goal when we were designing the clustering algorithm. And the other goal is of course speed.
What were the roadblocks over there though?
One of the roadblocks is finding images within epsilon distance of a point is easy on, Cartesian coordinates, when it's just a flat plane. But the Earth is not a flat plane. We want it to work for people in Alaska. We want it to work for people in Antarctica. You know, scientists should be using Dabble over there.
Very true, very true.
So if we wanted to work for places like that, we need to be smarter about how latitudes and longitudes are used to calculate distance. And so we have created an algorithm that effectively puts each image in one block of the Earth. So that's called a kernel. We take the set of images and we split them into a smaller set where each set is one set of images, and we only need to we only need to see images that are neighbors in this set. So by only checking neighbors, we optimize the algorithm down from almost 50 seconds to 10 seconds. Like, that's one of the best optimizations we've had. Of course, this is still in Swift. We are working on a C multi-threaded implementation of this. And given the Swift slowdown is almost 3x and the multi-threading slowdown is almost 4x, we're expecting a 12x improvement in clustering times.
Oh wow. So how fast can I then load the entire thing?
In less than a second.
Oh wow. So the 20 seconds that we had to wait initially, now will happen in less than a second.
Yes.
And that's how it should be.
So let's go back to explaining what this entire kernel spherical coordinate math is to.
So
Right.
for us, we have different zoom levels. At each zoom level, some set of images get merged together.
Right.
The distance threshold at which images need to get merged together is called epsilon. Now we need epsilon. We need to find all the other images for every image that are in an epsilon open ball next to it.
Right.
To do that, we of course use the kernel. We go through all the neighboring images, and we see which ones have satisfy the distance threshold of less than epsilon. And once we quickly do that, we're able to figure out which ones need to be merged. We will merge them multi-threaded, and we will figure out the set of effectively the stack of images that need to be displayed at each zoom level. And so because we have all of this pre-calculated, and when you zoom in, zoom out, everything is instant and it feels completely seamless.
Right. Yeah. Makes sense.
And we have to be smart about how we are splitting the kernel. So we're using angles and the latitude longitude to change the size of the kernel according to where you are on Earth, so that the neighbor logic always makes sure that any image within epsilon distance is a neighbor of your kernel spot.
Right. Yeah.
Well, I understood none of that.
Makes sense. Yeah.
But that's,
yeah.
that's why
Which
I
is
guess I
basic
have these guys.
trigonometry.
Oh, that's like a shot on me, dude. But that's fine. That's fine. That's why I have AJ and Heath to help me out with this. I think we can cut this part over here. So that kind of explains some of the math of Zoom. Did you get it at least?
Yeah, definitely.
Okay, fine. Clearly, I'm the dumb one here. But well, yeah, that cuts the pod on Zoom, and we will continue on to the next pod where maybe we talk about some of the other things we're working on Dabble.